Alright, on the bench, the HP 106B Quartz Oscillator, one of their better quartz oscillator. I think that's one of the best they made, at least at the time. It has a double oven inside, which makes it pretty good, and this one used to be owned by Celtic Technology in Laguna Beach. So if you are a former employee, let us know what you are doing with it. Hello and welcome back. If you follow the channel, you know that we just repaired an HP 115BR divider and clock, an instrument that was used to synchronize the world's atomic clocks for the first time in history in a famous 1964 flying clock experiment. This clock doesn't work on its own though, it is meant to be coupled to a super stable reference oscillator, crystal or atomic. We hooked it up to our HP 5061A Cesium atomic reference, resulting in this beautiful steampunk atomic clock, a close replica of the one they flew around to synchronize the world back then. But the cesium tube in the atomic clock has a finite lifetime, and although replacement tubes are still made 60 years later, they are in high demand and hugely expensive. So we don't want to run the clock off the atomic source on a continuous basis. However, we have the next best thing in the lab, the HP 106B Quartz Oscillator, a double ovenized reference standard. It was the highest stability reference oscillator in HP's lineup before the arrival of the groundbreaking Cesium clock. If we were going for the looks, we might want to use the 107BR, the mil-spec quartz oscillator, in the same hermetic enclosure as the clock, so they'd be matched exactly. But our civilian 106B, donated once again by patron John Pumpkinhead, has 10 times better stability than the already very good 107BR, and has the same special plug at the back to interface directly with the 115BR clock. And we can let this quartz oscillator run forever without worry. We may just resync the clock from time to time to the Fort Collins atomic signal, which is exactly how this combo was meant to be used. However, I doubt we'll ever need to do that if we just need regular time. This 106B 115BR combo should outperform common quartz clocks by well over 2 orders of magnitude and keep us synced to better than a second for many, many years. I cleaned it enough so that we can touch it, so I know that it has a little cadmium battery inside normally, but I can see through the perforation that it has been removed, and that would be good because those batteries usually they destroy anything that's near them. And I think this one is rated for 10 to the minus 10 long-term stability. Should look it up. And what do we have? Oh my, we have an oven of gigantic proportions. Double oven. Oh, that's no good. We have a cable that's not connected. These are the dividers, so similar to the clock that we worked on. There are some analog dividers. Power supply, battery used to be there, but I see the wires have been cut at the bottom. I can't see them, but believe me, there are cut wires at the bottom. I think you can see it, there are a few gears. Temperature 57.5, crystal serial number whatever, and it's units 5 and 24. It's in the 1969 catalog, but I don't know when it was born. I have to research that too. Probably early 1960s would be my guess. So what's behind the door? It's a little counter. Frequency adjustments in parts in 10 to the 11th. The crystal is 2.5 double for 5 MHz, then divided by 5 for 1 MHz, and divided by 10 for 100 kHz. I like on the instrument of that kind, there is 1 meter that tells you everything. Supply plus 18 volts, the quartz running, how much the inner oven, the outer low oven are the power that goes into it, and it's full scale at the beginning and then it goes down. And then if you have any of the frequencies, if the AC gets interrupted, you get a warning light that your continuous clock has been stopped. You have a slow charge and a fast charge that you can only put on a few hours. And it was a cadmium nickel, which means if I were to put some nickel metal hydride, I would have to change the charger circuit so it doesn't continually charge. So let me give it a rough clean so we can touch it, same as I do for the exterior. Usually I don't film this, but since the camera is here, I might run it on a fast motion. So first finding here, the card for the power supply is missing a few components, 1, 2, 3 transistors. That doesn't bode too well. It was used for parts, I guess. Okay, so fortunately we have the schematics for this thing, and the 3 transistors that have been removed have to do with the battery charging circuit. Actually, it's a regulator, and the battery does the 24 volt regulation. So it's problematic when you remove the battery. And then when the thing is run on battery, there is a latching relay that will latch when the voltage drops below 20 volts, so not to drain the battery. So, and they have removed those transistors. Hopefully the latching relay is in the right position, but that will only work without a battery if that is changed to a 26 voltage Zener instead of a 32 volt Zener. So maybe they've done that. We'll have to check. The 106BR is quite a refined instrument. The reason it looks deceptively simple is that a lot of the critical electronics are hidden inside the double oven cylinder. At the heart of the beast is a 2.5 MHz quartz crystal cocooned in the innermost of 2 temperature-controlled ovens. It is followed by an elaborate AGC control to make sure the crystal is driven with maximum care, then a doubler, then the dividers. There is a power supply outside the oven, part of which is on the board we just discovered. This supply is mainly preoccupied with battery charging, so it has more functions that you'd expect. It switches from current limited charge operation for the main charge to constant voltage operation for trickle charging. There is also a battery over discharge protection scheme, which will disconnect the battery via a relay if the battery voltage falls too low. This is to protect the NiCad battery from being drained too low, as this will kill them, much like modern lithium batteries. Finally, there is an AC interruption detection circuitry to warn the user that a power interruption has occurred. Note that downstream of this, there is a much more precise voltage regulator inside the oven for the critical oscillator circuits, so they are not affected by fluctuating battery voltage nor temperature. Since we are part of the nicely designed instrument appreciation group, here is a taste of the schematics inside the oven, so you can get a sense of it. Our crystal oscillator proper is over here, shielded inside the inner oven. Here is the 2.5 MHz crystal. It can be fine-tuned by 2 means. The so-called coarse tuning is via a variable capacitor, but as we saw, even this coarse adjustment is finely operated by the train of reduction gears. The super fine tuning is done via a varicap, a diode whose capacitance varies depending on the voltage applied, with the knob graduated in parts in 10 to the 11th. But that's not all. There is a whole complicated part involved in controlling the oscillator, which they call the AGC amplifier. You see all quartz crystals age with time, slowly lowering their oscillation frequency. But the more carefully you drive them, the more you will minimize the aging. So the oscillator uses the bare minimum energy to keep the quartz oscillating. The AGC circuit actively monitors the output of the crystal and then automatically adjusts the drive level to keep it oscillating via feedback control. You can tell how low the signal coming from the crystal must be. They need no less than 4 transistors to amplify it. And that's just the preamplifier. There is yet another amplifier after that, not shown in the diagram. Similar care is taken with the oven temperature control and the secondary 18-volt regulator. It uses a pair of matched Zener diodes and a differential amplifier stage to cancel out temperature effects that affects the Zener voltage. The temperature control is equally refined and complicated. But for now, we are mainly concerned by the more pedestrian main power supply, itself mostly concerned with the charging and safekeeping of the 24 volts NiCad battery. It uses a standard series regulator, transistor Q1 and Q2 in a high-gain Darlington configuration, reference to the voltage produced by Zener diode CR3, which is a relatively high 32 volts. But while charging the battery, resistances R11 and R12 monitor the charging current and will reduce the regulator voltage through Q3. That's to implement the constant current charging of the battery. Once the current dies off, the supply operates at a constant voltage set by Zener CR3, generating approximately 30 volts. The battery over-discharge protection is operated by the differential comparator Q4-Q5 and the latching relay K1. The pair compares the battery voltage to the voltage set by the matched Zener CR7A and CR7B. If the battery voltage drops below 20 volts, the pair flips, activates relay K1, and disconnects the battery from the rest of the instrument. K1 will only reconnect the battery when power is restored and supply voltage reads healthy above 20 volts. Finally, the AC interruption circuit is implemented with a silicon control switch, or SCR. When the instrument is first powered, the SCR is off, and that causes the indicator DS2, more on this one later, to turn on, indicating that there has been a power interruption. The operator then presses the reset switch, which turns the SCR on, meaning that it begins conducting. That will turn the indicator off. Once triggered, the SCRs keep conducting until the current flowing through them is interrupted. So the light will stay off unless a power interruption occurs, which is just what we want. So far it appears that Q3, Q4 and Q5 have been removed from the board, which may be related to the removal of the battery, but it's somewhat cheesy. You should not need to do that at all. It should just work all fine without the battery. The power supply will just switch to the constant voltage operation at 30 volts. So this is a bit mysterious. As we'll see, there is more to this story. Okay, on further inspection, what's produced by this is further regulated down in the oven, if I have it in the right direction, in plus 18 volts. So they refer to it at plus 26 volts. It's going to be more than that. It's going to be 30 volts without the battery. But I suspect it's still okay. It should still work with the transistors applied, so I'm not sure why they took them out. Okay, more discovery. First, this unattached wire is actually not a concern. That's how it's supposed to be. If you follow that, it goes to a plug at the back that says EFC. That's for electronic frequency control. You can actually phase lock that thing if you wanted to a Cesium, for example. And when you are not using EFC, you're supposed to short that output here, which is J6, and that's what this is. This is a shorting plug. It's all metal, so that the frequency of the quartz is not changed by any random voltage that develops in the cable. So that's all fine. Now I open the back and I have more interesting news in there. There is more modification to the power supply. Q1 has been entirely disconnected, and Q2 there's a resistor added in a precarious way, and is that a diode or something? So I haven't quite figured out what that is. And I found those two stickers in there, so it has been calibrated or looked at in 95. Okay, I've traced what is the modification they have done over here. They have taken all the transistors out and reverted to a single transistor regulation, and they have a resistor and a zener, which I suppose now is the right voltage, 26 volt or something. It's a little dodgy the way they did it. I would have preferred a capacitor in parallel with the zener. There should have been one. The original has a capacitor next to it. And while I was at it, I cleaned up the modification. I removed the diode and tested it, and indeed it is a zener. And nice zener. It's a 24 volts, 23 volt zener. So I reworked the modification to clean it up, so now the components don't flap in the breeze. I isolated this lead, I added the missing capacitor, I removed this hack of a job of a heatsink that A is not needed because it's only 120 milliwatts in the zener, and B is just, it probably didn't do anything. Alright, so I think we're ready to power it up. Okay. Do we have voltage? I should see 24 volts. I see 20 volts and 39 volts. That doesn't seem to be enough voltage here in the zener, but that should give me voltage at the output, which would be this guy, if I'm not mistaken. Okay, I have 20 volts. So, which is not 24 volts I was hoping for, so I need to change the zener. But then the circuit should still work. There is this special circuit. It's actually quite complicated. It has an SCR, and it will light up. No, AC interruption. It will not light up. It's only if I had AC interruption. Is that light here? So let me try it again. I should try to interrupt the AC. I pull it off, pull it back on, and then the light should come on. And it did not. So that's not working either. Okay. More debugging required. Actually, the built-in meter might give you some indication. So supply is not high enough because I have only 20 volts. 18 volts good. Oh, I'm oscillating. Inner oven, outer oven, 5 megahertz, 1 megahertz, and 100 kilohertz. So, you know, it might be working. I just need to adjust the supply and repair the AC interruption. It might be in better shape than I think. 5 megahertz. Oh yes. So I got 5 megahertz. Let's say it's 5. I got 1 megahertz, and I got 100 kilohertz. So the thing works, except the ancillary thing. Definitely have to bump up that zener. And then I have to figure out why the AC interruption circuitry doesn't work. Okay, I tried several zeners and none of them do work. I always get 20 volts across them, and I know what's happening. Is that they went too far in their modification. There is not enough gain in that transistor to bring it to 24 volts. So we have to actually reuse that circuit, rewire the first transistor and get back to the original circuit. I guess they never checked if that worked or not, but it doesn't. One stage is not enough. Well, guess what? I was going to press Q1 back into service right here, and before that I tested it, and it's dead. Never a dull moment on this channel. So, fortunately I had the exact same one in my collection. It's an 1854-0003. The third NPM transistor that HP ever identified in their collection. So I'm blessed to have the exact original. And I use the same wire color scheme. Okay, so we have a good Q1. Let me rewire it in the circuit as it should have been from the start. Green goes to green. So it's going to look exactly like the original once I'm done. So no more ugly modification. All right, and then blue. So look at it. They tell you the colors. The yellow wire. This one's the green wire. This one they don't tell you, but I know it's the blue wire. All right. So this is back to its original state. I have to change the zener on the other side. Yep. All right. Here's this colored resistors. I better check them all. And surprise, surprise! That resistor is blown up. That's the one right here. It goes into Q2, which I just repaired. So something catastrophic has happened to this board. Where is it? So it's a pretty poor looking resistor, this one. And the zener showed showed sign of having been changed too. Alright, new resistor, new zener diode, ready to go back in. Okay. And at the back here, there is no more modification. This is as it should be. See if we have recovered. Here we go. 22.85, so almost. So it takes 1 point, so I need a little higher zener diode. But it's much better, it means it's regulating now. Let me see what the voltage on the zener diode is. Can I look it up? Oh! And that's enough to get my AC indicator working. It's a tired neon, and then I do reset, then it's gone, and then my supply is much closer to what it should be. Alright, we're doing much better. So let me unplug it, replug it. Not enough to get my AC interruption, so it needs to go down longer probably. And we plug it in. No, not very reliable that signal. Okay, but it was. I bet you it's the neon that's not good anymore. Didn't have exactly what I needed, but I made an approximation with a pair of two that should give me 25 volts and should regulate around 24. All right, third time is the charm. Ah, 24.08 volts. We are good. All right, so that's dealt with. And my indicator is trying to work. So I think the logic is working fine. The logic is on the board we just repaired. But we have a weak neon. So this is a weird animal. It is a neon, which you can power with low voltage because it has a little oscillator that produces high voltage in it. And you can control it with a logic level. So it's the equivalent of an LED but with a neon. There must be a way to replace the neon in there, but it seems sealed. I don't see an easy way to take it apart. Okay, I found the catalog for this. It's a low LVN, this low voltage neon made by Tech Transistor Electronic Corporation, and they were a company specialized in indicators for computers in the 1950s, and they make all sorts of lights for blinking light panels. But this one doesn't have a replacement lamp, unfortunately, so that's a problem, and I couldn't find this exact model on eBay. I think I can MacGyver my way out. In my collection I have this little LED based indicator, which is a 5-volt thing, and it fits right there, and I'm just going to hook myself up across the SCR, which is the element that does the bistable thing, and it has like 30 volts across it when there has been a current interruption, and then there's 1 volt across it when it's conducting. So that should work with a drop resistor, 1.2K. So here's my final bodge on the board with my Zener, and then I did reuse one of the contacts that was liberated by the absent transistor to do my new indicator scheme. My poor low voltage neon is no more, has been replaced by an LED that looks the part. Time to test. So if we turn it on, we get signal, we have the AC interruption indication, we have 18 volts, we have the inner oven, the outer oven, they are cold, so they are off scale. We have 5 megahertz, 1 megahertz, and 100 kilohertz, which we can see all the way back there. And so the good thing with those quartz things, the older they get, the more stable they get. It's one of the rare instruments that bonifies with time. So alright, I let it warm up overnight, and now you see the outer oven is off the maximum scale, and so is the inner oven. And they are dancing a little bit, so I guess it's regulating correctly all the time. And this one will just move around, so they both fight each other. And I have brought my frequency meter, which has been referenced to the Cesium clock, but that's probably moved since then. But that will give us a first approximation to get it back into spec. Oh, there you go, this one moves things around. There we go. So note that they have a little counter here. So that allows you to track the aging of the crystal. And it was at maximum of the scale. If you're near to the maximum, you bring that one back down to about 1000, and then compensate with a coarse adjustment. But man, this is super fine. If you look at over here, it has hardly moved. Okay, so you're supposed to get it there. 2000. So we will bring the analog scope and the Cesium clock. Alright, always a good day when we get to pile up all the HP equipment. The Cesium clock is up and running, and I brought a scope to do Lissajous plots and comparison. So right now this shows 4999. The Cesium clock over here on frequency B shows the same number. So if I make the ratio, they are one and the same, but of course that's not enough decimals for us to know. So we're going to use the scope. So this is going to go to A, B, there we go. Well, we're already at a good place, it's not moving. So to a first order, we are doing pretty good. And I suspect if I make a Lissajous curve, it's going to not tell me enough. Yeah, XY is over here. Alright, so it's already nice and super stable here. So that's not going to tell us enough. We are going to reuse a technique I tried last time when I calibrated the Z-man line on the clock. So we do big crossings, all right, and we go as fast as we can. Oh, here we see it. So I'm just looking at the crossings of the two ways, but super magnified, and it's moving to the left. And let's see if we can get it to move to the other direction. Okay, yeah. So that button is doing something. I think it's worse. This is now in the other direction. Alright, so to first order here, they are aligned. I'll just wait maybe half an hour to see if that moves. Short term, they are just completely stable. The quartz oscillator can't keep up with the cesium clock, which is not normal. You hardly can do that with the oscillator in here. This is 10 times as good as a regular oven quartz oscillator, I would say. Alright, here we are 20 minutes later, and it's moved to the left, half a graduation, half a large graduation. So I moved it up to 1065 here, so that should quicken it a bit. We'll consider it calibrated. Hooray! We have our 106B back into action, so we'll reunite it with the clock and go through the clock adjustment ceremony. It's so comically complicated, it's worth its own explanatory video, but suffice to say, it's not something you want to do often. Plus, you wouldn't want to lose your atomic traceable time due to a power outage. Which is why the 106B came with a battery that could operate both the oscillator and the clock, and I really need to get that functionality back. I think I finally found a way that I can replace the battery and still use the old charging circuits by using a lithium iron phosphate battery, which you can trickle charge, and it uses the same scheme. It's first current charge and then a constant voltage charge at about 29.6 volts constant voltage, which is exactly what the circuit was designed for. So let's see if we can restore it completely to its first configuration, including the battery backup. So it fits perfectly. I could even fit two of those, which would give me 4 times the original capacity, because the battery originally has twice the original capacity. I'll need to put back the 3 transistors, go back to a 30.6 volt Zener, and find another way to route my wire for the light modification I made before. Okay, so my card is almost back to the original. By pure chance, I had 3 of the original transistors HP marked left. This is my only modification for the other indicator. And back under the instrument, it's back to its original configuration. I reconnected the relay as it should be, and the only modification I have is the extra wire for my new indicator modification, and that connects to the one I have added on the other side. Checking here. 2729. Oh, that's perfect. 2746. Okay, I was aiming for 27.6, so that's just very good. Okay, next step is to put the battery in. So turn that on. That's good. We have the AC reset. That's good. We have a low charging current. That's good. We have the high charging current, but not too high. And now, if we turn this off, battery takes over, 1/2 amp, still there. And then if we take this up again, we didn't have, well, we had the AC interruption signal, but we didn't get an interruption in the device itself. Ooh, that's pretty good. And one more thing we could test is low voltage protection. So I'm going to turn it off. I'm going to disconnect it. So now it's powered by the battery. I'm going to disconnect it. And the low voltage protection should turn off. And when I reconnect it, it should not come back on. It did not. But now if I do this, it will. And now it should work again. Yep, that works too. All right. And I chose just to use the regular packing material that came with it. Okay, now it's good. Clock. Oh man, those are so hard. Here we go. Okay, so at this point I do not have the battery because I disconnected it and reconnected it so it went below 20 volts and disconnected. So it's only going to reconnect once it has power. And it tells me I had an AC interruption, which is correct. Now I go reset, and now I'm going to just power it off. I put a switch right here. Boom, backup power is continuing. So I now have, I'm powered by the battery. There is no indication of it, by the way, except when I power it back on, it's going to tell me that there was an interruption of power. And then I can charge it some more, and I am good. I have it restored to full operation. And the reason you want battery backup, of course, is because you have your clock and you have spent so much time aligning it and synchronizing it. It's such a pain to start it that you don't ever want it to stop. So I'm going to check if that can be done. I haven't tried that yet. Let's see. Yeah, it's going on battery. So you can then move the clock, and then it will keep time, and when it comes back it just tells you it lost power for a while. But no big deal, it's still synchronized.